Hello, everyone, and welcome to our live session for today. What is this? July 31st, so the last day of the month. We are happy to be here. My name is Matthew. I am working on the behind the scenes stuff. I'm part of the course staff for our online classes, which many of you are students. Welcome to you. And for those of you who have found us through YouTube or through some other means, welcome to you as well. We're looking forward to your questions. Let me just go over the way that this works. Please post your questions in the chat. I will grab your questions from there. I promise we see all of the questions. Please ask your question only once. I will grab it from there. We try to go generally in order, but we do sometimes jump around to give a variety of topics and to give a variety of people a chance to have their questions asked. I think that if you have a chance, please like the video, hit that thumbs up button so that we can reach more people with these videos. And if there's anything else, I will cover that after Chris has a chance to introduce himself and welcome you all. And then we'll get started with a topic that he will have that will kind of, maybe spur on some additional questions. So with that, have at it, Chris.
Okay, welcome everyone to the Q&A live session for people in our course or anyone who finds us by some other means. I was going to start today with a topic that has been in the news in the last few months. It's sort of been overwhelmed by more urgent news in science because there's a lot of science news going on in the political side. It's about the search for the missing matter in the universe, and by which I do not mean dark matter, I mean the missing normal matter. So in the composition of the universe, the pie chart, if you like, of the universe, 65% of the universe is dark energy, something we don't understand very well. About 26%, 24% is dark matter, something we also don't understand very well. And the last 4% is normal matter, baryons as they're called in physics. And those baryons are, of course, protons and neutrons and electrons and small number of subsidiary particles. Those are stuff that are made up of all the atoms in our bodies and in the planets and the stars and the galaxies in the universe. And it might seem like we would understand where that material is, but it's not true. All the stars and their surrounding planets, which are a small fraction of that mass, so all the stars and all the galaxies in the universe really only account for about 10% of that baryonic material. In other words, if you're doing the math, that's like about 0.5% of the physical universe. Not very much. So 90% of the normal stuff has sort of been missing. Now that has changed a little over the years because we found that some of that material is in the extended halos of galaxies, not in the stellar core of the galaxies. But that still left most of the baryons, 80% of the normal matter, the baryons, missing. And progress has been made on that. A little bit using X-ray methods over the past few decades. I was involved in some of that work. And then very recently with fast radio bursts as a probe or a tool. And pretty much the problem was solved by this method. So astronomers have been studying fast radio bursts and trying to understand that physical phenomena. But in this case, the nature of the physical phenomena doesn't really matter. All that matters is that these are radio beacons shining large distances across the universe and detected by radio telescopes. And basically the method that was used was to use the fast radio bursts to illuminate diffuse, very diffuse, and it turns out very hot matter in the space between galaxies and try and measure how much there is. And it's turned out to be a very successful technique because that matter, that very diffuse and hot matter, slows down the radio bursts in a very well-measured way, in a way that you can use to calibrate how much stuff is out there. And that succeeded extremely well to the point where the fast radio bursts have identified that the remaining missing mass is in the intergalactic medium. It's in the space between galaxies, very weakly clustered, a very low density gas, but also very hot because it's irradiated by hot stars and starbursts in galaxies. So this is a very big success to have found where the missing normal stuff of the universe is. And then we can get on to the bigger issue of where the missing dark matter is, and that's a whole nother can of worms that I've talked about in a number of live sessions.
Excellent. Well, thank you very much for that introduction. So, if anybody has questions about that missing baryon matter, please post those in the chat and we can cover those. In the in the interim, we'll start with some questions that have already been posted in the chat. And the first one today is from AKA The Best. Hi, Professor. I wanted to ask, why does antimatter even exist? Why not just matter?
Yeah, it's a good question. Why should there be two different types of matter with opposite quantum properties, essentially? I mean, there's two answers to this question. One is a theoretical answer, which is that out of the theory of quantum mechanics from the early 20th century, it became clear that there were two solutions to the wave equation, two solutions to the understanding of how particles and radiation exist in the universe, and they were symmetric but had opposite quantum properties, such that a positive electrical charge for one thing, the particle, would be mapped to a negative electric charge for the other thing, antimatter. So antimatter is a prediction out of quantum physics. And it was another 15 years, I think, before Philip Anderson, experimental physicist, detected a positron in a cloud chamber experiment. So antimatter was indeed detected back in the middle of the 20th century. So it's predicted physically to be a symmetric counterpart to normal matter. And then the operational question is, why is antimatter so rare in the universe? Part of the reason is simply because anytime antimatter exists, it quickly meets normal matter and annihilates to create gamma rays. So antimatter does not have any longevity in a universe filled with matter. The reason why there's not equal amounts of matter and antimatter is also to do with quantum physics, and it's also to do with the conditions in the early universe. And that's a still unsolved problem in theoretical physics, why there was this slight asymmetry between matter and antimatter early in the history of the universe. But having had that asymmetry set up very early after the Big Bang, then it becomes natural to understand why the universe would be overwhelmingly made of matter, with antimatter just rarely and fleetingly produced out of pure energy in physics reactions.
The next question is from Karen, who's on with us live, who has a related question. I thought I would just jump to this one. Can you talk about what is the difference between antimatter and dark matter?
They are different. Antimatter is the symmetric, almost perfectly symmetric counterpart to normal matter predicted by quantum physics and observed in the lab and elsewhere. But it's normal stuff. It's the stuff that we understand as baryonic material or antibaryonic material in the case of antimatter. Dark matter is something else entirely. It's something we don't totally understand. It has mass, but whatever it is does not interact with radiation. Whereas normal matter, normal atoms, do interact with radiation, and that's a lot of physics is about those interactions. So it's really something quite different. There's no direct relationship between dark matter and antimatter. It is indeed, however, possible that if the dark matter is a fundamental subatomic particle, that particle will have an antiparticle twin. But since we don't know what the particle itself is yet, that's jumping ahead of the game.
The next question is from Glenn, who's on with us live, who would like to know, I'm always amazed by your breadth and depth of knowledge. How are you able to achieve this mastery?
Well, it's very flattering. Thank you. I mean, I'm curious, of course, like all scientists are curious. I do spend a fair amount of time reading. I read research papers in my field, and I try to stay broad. So, as any of you can do, and I recommend this, read the science magazines, the general science magazines. So I get a lot of my information from reading Science Magazine itself, which is a publication of the American Association for the Advancement of Science. I think a subscription costs $100 a year. It's not trivial, but it's a very good investment if you're interested in science. Many of the articles are technical, but there's also news, policy, education, and nice summaries of the technical articles so that you don't have to digest all of them. So that is a primary source of how I learn about biology, about genetics, about chemistry, about other things than physics and astrophysics. And then, of course, I read, various news sites that have science news and so on. And I probably spend about an hour a day doing this. So, to keep up with a fast moving field of science when it's beyond your own field of astronomy, it does take a little bit of time, but I think it's time well spent.
Excellent. Thank you very much. The next question is from Adrian Murray, who had got some idea from the TV series Doctor Who and wants to know if there's any sort of truth to the idea that matter is simply congealed or condensed light.
Um, Not really. That's not a very meaningful physics idea. A matter interacts with light, but light is essentially photons, and photons do not have identities, such that you can even easily count them, whereas particles do. You can number particles, you can count them, you can weigh them, and so on. So matter and light really have quite different properties, and there's no way to sort of compress light, if you like, and form a concentrated version of it that becomes like a particle. So these are so profoundly different at the level of basic physics that I don't think we can think of matter as congealed light, although I do like Doctor Who as a series. I've enjoyed many of the series, going all the way back to the original one in the mid-1960s when I was a kid in England.
Excellent. Thank you very much. The next question is from Ernest, who is on with us live and would like to know what is string theory and how can it tie together general relativity and quantum mechanics in one grand unified theory?
So string theory is a frontier physics theory, and it's not really just one thing. Physics, it's become well enough explored after really 45 or almost 50 years of theoretical investigation that it's not a single theory. It's a set of theories, interrelated theories. And they basically say that particles as we understand them are not fundamental entities, but they're composed of tiny one-dimensional strings whose physical nature would only manifest on a size scale and an energy scale many orders of magnitude smaller and higher in terms of energy than anything we can diagnose directly through physics experiments. And that's part of the problem. It's a huge desert of phenomenology between the highest energy of our accelerators and the energy that would liberate the physics of string theory. So it's remained pretty much a purely theoretical concept. It does indeed, by design, try to reconcile these two hugely successful theories of physics of the 20th century, general relativity and quantum mechanics. And it's an unfinished project, an unfinished endeavor. It's very difficult to work with the theory mathematically, and it's not had great success in making unique predictions or being testable in the lab, in part because this difficult reaching down to a size and an energy scale that are really inaccessible to laboratory experiment. So I'd say there are many pretty hard skeptics now about string theory, about whether it's a meaningful way forward for physics. The people who work on it insist that it's a beautiful and elegant theory that has great promise, and they're willing to keep working on it. And that's sort of where things sit, and they haven't really changed or evolved very much, I would say, in the last 10 or 15 years.
Excellent. Thank you for that explanation. The next question is from Terrence, who's on with us live. If water molecules exist in the Goldilocks zone of Mercury's atmosphere, would it be possible to have, they say photocopies of DNA, but would it be possible for DNA molecules to form and exist there?
So Mercury doesn't really have an atmosphere. Mercury is sort of like the moon. It's an airless or a planet of such small mass that it cannot retain an atmosphere. Mercury does have a temperate zone. I wouldn't call it a Goldilocks zone necessarily, but the terminator, since Mercury is tidally locked in its orbit of the sun, so always presents the same face to the sun, there is a boundary between the eternally sunlit side and the eternally dark side, which is extremely cold without the atmosphere. Temperatures plunge hundreds of degrees across the terminator. So in principle, there's a very slender region, the terminator, where the temperature is temperate, sort of the temperature of a room temperature. But it's not a room temperature because there's no air, there's no atmosphere. So because there's no atmosphere, there can't be water vapor. And then we know there's essentially no water vapor on Mercury. We've had remote sensing to say that it's basically baked dry by the sun, as you would expect, given how close it is. So there is not really any habitable location on Mercury, even though it has this interesting terminator region.
Excellent, thank you. The next question is from Wendy, who sent an email, who would like to know if the Oort cloud is hypothetical, how can astronomers give it a distance of 2,000 to 100,000 AU, and how can we sort of give it a location if it's hypothetical?
Right. It is hypothetical, but not completely hypothetical. And the reason we can give it a distance and a size and a scale is because the premise of the Oort cloud is that it's a repository of perhaps 1 trillion comets that spend most of their time in deep space, distances of 50, 100, 200,000 astronomical units, and then occasionally come in on looping elliptical orbits into the inner solar system. And that's, of course, how we can infer its existence. So we do see comets with highly elliptical orbits traveling through the inner solar system, and just from their orbits, we can infer that they will be spending most of their time, given Kepler's laws, very far from the sun, and therefore most of their time very far from the sun. So the very small fraction of comets we see on highly elliptical orbits coming to the inner solar system are the sort of tip of the iceberg of a huge population of comets spending most of their time at very large distances. So it's this inward, this transient visiting population of Earth crossing and inner solar system crossing comets that allow us to put numbers on the size and potentially the mass of and the distance to the Oort cloud.
The next question is from Z Jingostani, who's on with us live, who would like to know, has the search for Planet 9 now officially stopped, or are there some physicists and astronomers still looking for it?
There are still people looking for Planet 9. Planet 9 is a hypothetical large planet in the outer solar system. Now, another news story in the last few weeks has been the discovery of more sort of trans-Neptunian objects. That is to say, large planets, large enough to be almost called planets, so they're about Pluto size or maybe larger. And they're on highly elliptical orbits in the outer solar system. They don't amount to Planet 9. Some people have argued that the nature of their orbit suggests a larger object further out on a stable orbit that could be Planet 9, but that's contentious. So I think the newly discovered objects that we're finding in the Kuiper Belt have neither confirmed that Planet 9 exists nor completely ruled it out, so people are still looking.
All right, so we cover this topic from time to time, but it's been a few sessions. But I will mention to anybody who does not get their sort of profession of astronomy questions answered, we have talked a lot about how one becomes an astronomer, how one studies astronomy in school. So check out some of our previous live sessions. That being said, we'll take one of those today. And this one is from Dan, but again, several people have asked similar questions. I'm interested in studying astronomy and astrophysics as a major or minor. Where do I start with that?
Astronomy as a major is slightly unusual. There's not that many departments around the United States that offer astronomy as a major. We do in the University of Arizona. We have a lot of majors. We have almost 300 majors. So I think that's the second largest in the country. University of Washington also has a lot of astronomy majors, and the University of Texas at Austin. Those are perhaps the 3 largest programs. But more generally, what you'll find is physics, where there is some astronomy in the curriculum. And indeed, about 2/3 to 3/4 of our astronomy majors are double majoring in physics. So if you want to study astronomy, you have to recognize that your diet is going to include a heavy dose of physics and math. That's just what it is, because astronomy is basically astrophysics. It's physics applied to the universe as a whole. And that's true of our program. Even an astronomy major, they will take more custom built astronomy courses, but a lot of their curriculum is physics and math. So I would look for a strong physics program that has a department with astronomers on the faculty, and that will guarantee that they're offering astronomy courses, so you get a good dose of astronomy. There's no reason not to do an astronomy major because, again, you'll be getting a lot of physics anyway, and that gives you an employment option if you choose not to go into astronomy.
Excellent, thank you. The next question is from one of our live participants. Arif Roni asked, so there was yesterday, I believe, a joint NASA India mission launched called ISRO or ISRO NISAR. It's a synthetic aperture radar satellite. Are you familiar with that? And can you talk a little bit about some of the unique aspects of that mission if you are familiar with it?
Yeah, it's an exciting mission, and it's a very good collaboration with NASA and the Indian Space Agency. And the Indian space program has advanced rapidly and impressively in the last decade or so. I'm sure you're aware India has had a lunar, put something on the moon. They had a private astronaut who sort of paid his way on the Axiom 4 mission just in the last few weeks. That's their second astronaut. So they're moving pretty fast. This satellite is an impressive Earth-looking satellite, and it's going to monitor the entire planet, and it's going to take observations, I think, over the whole planet like every week or so. And it's basically going to map changes in surface topography and geography, and basically be able to monitor changes to the planet. So we are changing the planet rapidly with climate change, with degrading natural environments, with loss of biodiversity. And this satellite, this joint mission, is going to be really important for monitoring the health of the planet in all sorts of ways. It's going to look at the way how fresh water is distributed, how deforestation is happening, how resources are being used by measuring the reflectance and the spectroscopy of the ground emission that comes back to the satellite. So it's a very powerful project for monitoring the health of planet Earth.
The next question is again from one of our live participants. Jane Weidman asks, is the universe optimized for the production of black holes?
That's a good and interesting question. Black holes exist in the universe. It's not clear if the universe is optimized for the production of black holes, but certainly the universe contains all the necessary ingredients for the formation of black holes. Obviously, the creation of black holes is driven by gravity. So gravity is a ubiquitous ingredient of the physical universe on all sorts of different scales. And a black hole is just the ultimate expression of gravity in a situation of highly concentrated mass. To get that to happen, you need special conditions, and actually you need quite a lot of time. So in the sense that the universe is large, filled with a lot of matter, and has existed for billions of years, yes, the universe is well situated to form black holes, because that might not have happened if the universe had expanded very rapidly and matter was too thinly diffused to collapse into things like black holes, or if there wasn't enough time for mass to aggregate and form things like black holes.
The next question is from Harali, who asks, can you share your thoughts on the interstellar object which is heading towards Earth and the latest news about it?
Well, we've had 3 genuine interstellar visitors to the Earth, and we don't understand too much about them. Of course, the nature of their hyperbolic orbits is that they are visitors, they're transients, and so we learn what we can while they're here, and then they move swooping away at very high speeds back out of the solar system. So each of these objects has told us interesting things. The one that got the most attention some years ago was Oumuamua, which is highly elongated comet-like object that led to claims that it might be an interstellar or a sort of artificial object from an alien civilization. That's been more or less debunked. So each of these interstellar visitors is interesting because it tells us that matter and objects can travel between solar systems. And that's interesting in its own right. It leads to, for instance, the idea of panspermia over whether life, that maybe microbial life that's trapped inside a rock, a meteor or something, or a comet, can actually travel between solar systems intact and seed life from one solar system to another. People thought that was a very unlikely thing to happen, but as we find more interstellar interlopers into our solar system, we have to take that possibility seriously.
The next question is from Hernan Reyes, who sent an email. There is a kind of an explosion of satellites, in particular these SpaceX Starlink satellites, which have done a lot of good for connecting people to the internet. Yet astronomers have voiced serious concerns. How will astronomy in the long run cope with all this pollution of orbital space around the Earth? Is there any planning underway to limit how many satellites private companies can send into space?
The short answer is no. This is a completely unregulated industry. It's an international industry, so there's no international regulation from the UN or the International Aviation Authority, which really only deals with aircraft, not with spacecraft. So there's no regulations within the US or outside the US. And so it's a problem because people are driven, companies like SpaceX are driven by commercial motives and profit motives, and they don't necessarily care in the short term whether they are spoiling the environment for themselves and for everyone else in the end. It's not a crushing issue yet with the number of satellites that are up there. Number of NERO satellites, I think, is over 30,000, but it's heading towards 60,000 or more by the end of the decade. And that's a point where collisions between them or will start to occur, generating a lot of debris, where light reflecting off them will start to spoil the images from our frontier telescopes. That's already happening with the Vera Rubin Observatory, and also is interfering with radio observations. So there are companies that are aware of the problem. SpaceX is aware of it. They pretend or claim to be working with astronomers to try and resolve some of these issues, but basically they're just going full steam ahead.
The next question is from Anjali, who asks, do you think that another ice age could happen again, either because of human-caused climate change or due to other sort of natural motions of the Earth, Moon, Sun system?
It's almost certain that there will be another ice age or more ice ages in the future. Currently in interglacial, which implies we're between ice ages, and that's indeed the case. It's been over 10 millennia since the last ice age. But however, orbital variations in the Earth, Sun, Moon system have sort of impute into the climate cycles that have timescales of 10,000, 40,000, or 100,000 years. The direct link to ice ages is not one-to-one and linear, so we can't predict ice ages like clockwork. But undoubtedly, these orbital variations are responsible for these climactic changes like an ice age. So we can't really say when the next ice age will occur, but they will be happening in the future. Climate change, as we're doing it, of course, is heating up the planet, not cooling down the planet. So it's driving us, if you like, away from another ice age. But the forces that might lead to an ice age are in the end actually more powerful than the human interventions that are leading the planet to get warmer.
Excellent. Thank you very much. The next question is from Jim, who would like to know, can you please talk about any time dilation between the Earth and the Moon? Like, is there any sort of effect of time dilation that we can observe on the scale of our local Earth-Moon system?
So there's a time delay from the Earth to the Moon just by light travel time. So that distance of 400,000 kilometers, 250,000 miles, means there's a light travel time of about 1.25 seconds. And so Yeah, you could hear it in the audio from the Apollo mission that when the mission control was talking to them, there was a sort of awkward 2 to 3 second gap because that's how long it took the radio transmission to go to the moon or to Apollo and then back again. So that there's a time delay. There's not actually time dilation. Time dilation is a term out of relativity, special relativity, and that only occurs when the relative motion of two objects is very high speed or a large fraction of the speed of light. And the relative Earth moon motion is not large at all. It's just tens of kilometers per second. So there's no formal time dilation involved in signals to and from the moon.
The next question is from Mihek, who asks, can you describe and explain the causes of an Einstein ring?
Sure. Einstein's theory of general relativity predicts that mass will bend light, and that's been amply confirmed. So gravitational lensing is the phenomenon whereby mass, which could be visible mass like stars in a galaxy, or dark matter itself, bend light. And so astronomers, starting with the Hubble Space Telescope and now with ground-based observatories in James Webb, have found hundreds of examples of mass bending light. Basically, large galaxies bending light from behind them and magnifying and creating distorted images, or more particularly, clusters of galaxies acting like huge lenses. So gravitational lensing is a big phenomenon. Give me the root of the question again.
Sure. The root of the question is, can you just describe and explain the causes of an Einstein ring?
So an Einstein ring is a very particular example of gravitational lensing, and it occurs when the alignment between the lensing object, say a galaxy, and the background object in us is perfect. They're all in a straight line. And that means the gravitational deflection of mass bending light is symmetric. And if you map symmetry of a bending angle around a circle, you get a ring. So a point is turned into a ring by that deflection. So in the object plane, it's an object that is a point source. But in the image plane, because of that deflection angle being constant with azimuth around 360 degrees, you end up with a ring. So it's a perfect alignment between a lensing object and a background object and us.
All right, the next question is again from one of our live participants. Sorry, let me get to the next one. Ali asks, how do astronomers measure the distances of stars and galaxies?
Distance measurement is a tricky thing in astronomy because there's not a lot of direct handles on distance. What we measure trivially in astronomy is position in the sky, the angle of something in the sky in two angles, and its brightness in radio waves or optical light or whatever wavelength of radiation we're looking at. Those are the things that astronomy easily measures. Distance is harder because we have to have some clue to the nature of the object. So distance measurements in astronomy are direct when we're dealing with the nearby universe, because then we can use the motion of the Earth around the sun to create triangles and do a parallax measurement, which is essentially just angles in a triangle. So it's direct geometry. And we now can use that trigonometric method, that geometry method, to measure distances out to a few hundred light years, maybe 1,000 light years. That's a lot of stars. So we do know the distances to stars very well by that method. Beyond that, we have to use other methods, and they involve knowing the fundamental physical nature of an object. We have to know something about, say, a supernova, how absolutely bright that radiation is, and then we use the inverse square law to relate how bright it intrinsically is to how bright it appears, and the inverse square law gives us the distance. So that's typically how we measure distances beyond the level we can use direct trigonometry.
The next question is from Boss of Clips, who's on with us live. The base of the question is factually incorrect as far as I know, which is, can you tell us the latest news about the star of Beetlejuice, which has exploded, but I think it's just people have been talking about it exploding because it's still there in the night sky. So can you talk a little bit about why people think it might explode and how a star could explode in the first place?
Right. And then there's a sort of interesting conceptual issue here, which is that to be totally honest, Betelgeuse might have exploded because it's, I think, 1,500 light years away. It will take 1,500 years for that information to reach us. So it's possible that Betelgeuse in the actual physical universe exploded a few centuries ago, and that information is still on its way to us. It'll be a millennium before we hear about it. That's unlikely. Betelgeuse is a very massive supergiant star that's near the end of its life. And the end of a star's life of that mass, it goes through instabilities and eventually will die as a supernova, so a cataclysmic explosion. Our observations of Betelgeuse are not precise enough, and our understanding of stellar physics is not detailed enough to use what we know about Betelgeuse to predict when it's going to go, when it's going to explode, when it's going to die. But we do know that it's near the end of its life. By near, what does that mean? Could be 1,000 years from the end, 10,000, 100,000. I mean, these are long times, but in a star's life of millions or billions of years, those are short times. So that's the situation we're in. We know that it's becoming unstable, which is a natural phenomenon when a star of its mass is at the end of its life, but we have no direct sign nor way of measuring the imminence of its eventual demise. But as we speak, it hasn't died, unless, of course, it did die and that information is still on its way to us.
The next question is from Dawn of the Force, who's on with us live. Do you think that the Vera Rubin Observatory's massive data stream will challenge the way that astronomers work, perhaps requiring more machine learning and less traditional observing? And how will it contribute to the search for dark matter?
So there are two different questions about the data stream of the Rubin Observatory. Yes, it's an enormous data stream. It's tens of terabytes a night. And the whole project was designed around data pipelines where it was known that it would be impossible to fully process all the data that the Rubin Observatory generates. Remember, the Rubin Observatory is observing this entire sky every few days to Hubble-type depth and looking for things that change. So in a sense, since you're looking for differences, you don't have to store all the data. You can subtract the data and look at differences. Also, since most of the sky is blank, dark, or just noise in the detector, you can, in a sense, throw away most of the pixels of an image and not lose a lot of information. So both methods are being used. The Rubin Observatory has pipelines that in super fast time will try and filter out the objects in the image and information about them and not save the entire images each time it takes one. I mean, they will be backed up. I mean, storage is cheap enough now that they can actually save the data. But as far as understanding it and reducing it and getting science out of it, you have to accelerate the process, which means generating object catalogs and then looking at differences in their brightness from one night to next, or a week to next, or a month to the next. And that's essentially how it'll work. And AI methods are indeed used to help facilitate discovery, because even when you get to throw away most of the pixels that don't have useful information, and that reduces your data rate, you still have hundreds of millions of objects in the night sky, billions actually, that are mostly not interesting or mostly not changing. And so you want to home in on the ones that are interesting or doing something unusual you didn't expect. And AI methods are already being used for that and will be increasingly in the future.
The next question is from Christina, who sent an email. What exactly is the purpose of a neutrino in the grand scale of things? About 10 to the 14th neutrinos pass through every square meter of space, but to do what exactly? It feels like a waste of potential if they don't play a role in something bigger.
Right. So neutrinos are part of the standard model of particle physics. And so they do have a place in the schema of particle physics. Their particular role is still not completely determined because we haven't successfully measured the mass of neutrinos. We know there are three flavors of neutrinos. So in the light particles in the universe, that is not the protons and protons and neutrons, which are basically made of quarks. Those are massive particles. There are light particles, leptons, or medium mass particles, mesons. And the light particles include electron, of course, the electron neutrino, and the tau neutrino. So there are three flavors of neutrino. out of the standard model. And this is just the schema we have in particle physics, and nobody knows why there are three generations of neutrino, because there are different masses too. The tau neutrino is more massive than the electron neutrino. So it does have a role, but I don't think we have a fundamental answer as to why neutrinos exist at all. And since we haven't measured their mass directly, that really limits us understanding them physically.
The next question is from Danielle and Sebastian. If our universe is expanding, why do some people think that we might be inside a black hole?
Well, some people have wondered whether the universe as a whole is bounded by a horizon. Now, the universe does have a horizon in the sense that there's a limit to how far we can see in space, given the age of the universe. So we can only see as far away as light has had time to travel in 13.8 billion years. But that's a horizon, that's a viewing horizon. It's not an event horizon. So it's kind of a mistaken concept to say that the expanding universe is acting like a black hole and therefore has an event horizon. So I think this is misapplying a concept from black hole physics to cosmology, and you see it quite often, but I think it's physically an inappropriate mapping to do.
The next question is from one of our live participants. What discovery would convince most cosmologists to abandon the standard model? Like, what would it take for physicists really to abandon the standard model?
I mean, it's an interesting question because every now and then we read that the standard model of cosmology is in trouble. I would say it's not in deep trouble, but it's got some problems around the edges. So what would it take to really pull apart the model? It would take for example, some evidence that the Big Bang didn't actually happen, that perhaps we've been misled about the nature of the microwave background radiation, although that doesn't seem to be the case. If for some reason we found out that the microwave background radiation had a local source or had some different source other than the origin of the universe 13.8 billion years ago, that would bring down the standard model. Another thing might bring down the standard model is if we found out that our inference of the properties of dark energy and even dark matter were just wrong in some way, that we misattributed their role in the universe and its evolution because we didn't understand them physically. That also could bring down the standard model. A third reason that the standard model would be in trouble was if we age dated an object. We found the oldest object we could think of, a globular cluster or the oldest galaxy, and we convincingly demonstrated by astrophysical methods that didn't involve cosmology that those objects, or that object, was more than 14 billion years old, 15 or 16 billion years old. Because in the expanding Big Bang universe model, the universe is essentially 13.8 billion years, and you can't change that number very much. So if you find an object that's by age dating older than the universe that contains it, then you've brought down the model. So that would be perhaps the most dramatic way of bringing down the Big Bang model.
The next question is from Anto, who's on with us live, who asks, is it possible that there could be anti-dark matter, just like there's anti-regular matter?
Certainly. Dark matter is inferred to be a fundamental subatomic particle. That's because we've ruled out other objects. We've ruled out physical dark objects like black holes or substellar objects or free-floating planets or dust particles. So we've ruled out particles and objects, physical dark objects on different scales, and we're left with a fundamental subatomic particle. Since essentially every subatomic fundamental particle has an antimatter counterpart, sometimes the object is its own antimatter counterpart, but generally there is a counterpart. So a proton and an antiproton, a neutron and an antineutron, an electron and a positron, a neutrino and an antineutrino. And therefore, we might anticipate that the dark matter particle, say it was a neutrino, which is an extension of the standard model of particle physics, there would be an antineutrino. So yes, it's entirely possible within the idea of quantum theory and the standard model, the dark matter particle will have an antimatter counterpart.
The next question is from K, astronomer from India. The overall question is pretty simple, yes or no. Is there another planet like Earth where life exists? But can you maybe expand on that and talk a little bit about other planets that we have discovered? What's the most Earth-like planet that we have discovered, and what are the chances for life on one of these other Earth-like planets?
So, no, we haven't found a planet like the Earth with life on it like the Earth. We haven't found life anywhere else, basically. That's the simple statement as of 2025. As for the most Earth-like planet we found some that are pretty close. We found planets that are within 20 or 30% of the mass and the size of the Earth that are in the habitable zones of their stars, and therefore they could have liquid water on the surface. And so that's pretty Earth-like. What we don't know for those planets, and there's more than a few of them, there's probably a few dozen of them, what we don't know is what their atmospheres are made of, because that's a much more difficult measurement. We've only been doing those kind of measurements for a few years, and so far not really on Earth-sized planets, more on massive planets like Jupiter's and Neptune's. So yes, we are finding Earth-like planets, and eventually, we look hard enough, we're going to find a ringer. We're going to find pretty much an Earth clone. It won't be a clone down to the level of detail, but in terms of global physical properties, it will be as close to the Earth as we can imagine. Does that in turn mean that there would be life on that planet? Well, that's a huge question. We'd love to know the answer. Astronomers tend to think, yes, if all the ingredients are there and there's plenty of time for life to evolve, then life will evolve. But that's pure conjecture. So until we find the first example of life beyond Earth, we simply don't know if Earth-like planets are like Earth in having life on them.
The next question is from Tanya, who's on with us live, and it's kind of a throwback to our earlier discussion about time dilation. What aspect of gravity is responsible for the phenomenon of gravitational time dilation? And can we measure this change in time using very precise instruments on Earth?
So, gravitational time dilation is caused by gravity. Essentially, time slows down in a strong gravitational field. So it's a very direct consequence of the general theory of relativity. It's a space-time property, if you like. When gravity is stronger, time goes slower, and we've measured this directly. We've measured it even in the fairly modest gravity of the Earth. That time dilation exists at a very tiny level for something like the Earth. Its most extreme version, of course, is the time dilation as towards the event horizon of a black hole, where time freezes at the event horizon. That's ultimate, infinite time dilation. So time dilation is a mathematical prediction straight out of general relativity that's been confirmed in a number of physical situations.
The next question is from the Pickers Institute, who's on with us live. In reality, how close are we to space travel and conducting studies and research in, let's say, just our own galaxy?
Well, we're not very close at all, actually. If you think about human travel in space as opposed to space probes, we've sent 5 man-made objects outside the solar system now. There are distances of 10 to 20 billion kilometers, well past the orbit of Neptune. So we've certainly sent space probes outside the solar system, but not really very far. Tiny, tiny fraction of the distance to the nearest star. As far as humans, of course, we've only ever sent 24 humans in orbit over the moon, and 12 landed and walked on the surface. And that's a tiny distance. That's a tiny fraction of the size of the solar system. So in the big scheme of things, and that happened over half a century ago, so looking at that rate of progress, you would have to say it's going to be centuries before humans leave the solar system. And I think that's a fair bet. Our travel through space using chemical rockets is just too slow. So to go to a nearby star with current technology, even huge energy requirements are required to go to a few percent of the speed of light. It'll take multi-generations. It'll be hundreds of years, decades or hundreds of years to get to the nearest stars. So humans will have to develop a hibernation technique, suspended animation, to even do that trip. And we're not very close to that either. So for all these reasons, I'd say space travel beyond the solar system is is very far away. Space travel in general is in its infancy, and so this is not going to happen in any of our lifetimes.
The next question is from Angelo, who is on with us live. Professor Impey, if the graviton exists, could there also be an anti-graviton?
So, not necessarily. A graviton is a hypothetical exchange particle. So, in the schema of physics, fundamental forces have exchange particles that carry the force. That's the way physics tends to think of it. So, the electromagnetic force is carried by photons. And that's a good example because photons don't have there's no such thing as an antiphoton. So, in a sense, partly for that reason, it's quite probable that if a graviton does exist, which is the force carrier for the gravity force, that there will be no anti-graviton. Because as you might imagine, that could lead you to wonder whether anti-gravity is possible. And there's pretty strong physics arguments and even some practical experiments that argue that anti-gravity is physically impossible.
The next question is from David Goldmeyer, who asks, what is the science? It's probably less science, more psychology. Well, I mean, I guess it's science, but it's not astronomy, but it's more psychology. What is the sort of phenomena behind the full moon appearing very large at the horizon?
Right. This is a well known sort of perception issue. When the full moon is high in the sky, you have no reference for its angular size. There's no nearby reference point. The stars are very faint and they don't provide a strong reference point. When the moon gets low near horizon, then it has a reference point. Also, you have refraction occurring in the atmosphere. So there's a perception issue and then a real physical issue. The real physical issue is that refraction can, in some cases, magnify an image down near the horizon viewed through a thickness of the atmosphere at that level. The perception issue is that when tethering an object like the moon, where you don't really know intuitively its size, to a horizon that you understand, like a range of mountains, it tends, for psychological reasons, just to make it seem a little bigger when it's low in the sky. It's been documented by psychologists. I think the fundamental reason why it appears larger as opposed to the same size or smaller is not completely understood.
This next question is from an email. It's kind of provocative, and I mean, ultimately, it asks you to sort of defend radio astronomy. How useful have radio telescopes proven to actually be? I think the premise is that we have yet to use them to discover life beyond Earth, but I think they've been useful for other things. Can you talk about like what have we gotten from radio astronomy? What has radio astronomy done for us
Right.
lately?
So the thing where radio astronomy has not succeeded is, I think, as the question's alluding to, SETI, the search for extraterrestrial intelligence. So we've looked for artificial radio signals from extraterrestrial civilizations, and in 60 or 70 years of searching, we haven't seen anything. So that's been a failure. But radio astronomy as a whole, which now is getting on for a century old, the first serious radio telescopes happened out of radar research after the Second War. And by the 1960s, there were radio telescopes being built in a number of places. Radio astronomy has been very successful. It's done, for example, going back to the 1960s, was the discovery of pulsars. And that required radio astronomy. So pulsars are the evidence that neutron stars exist. So radio astronomy had an enormous success in the 1960s, leading to a Nobel Prize in the detection of pulsars, which are neutron stars with hot spots. So that was a great early success. Also in the 1960s and through into the 70s, radio telescopes found that the nuclei of some galaxies were emitting enormous amounts of synchrotron radiation, which is a high energy radiation from electrons spiraling in magnetic fields. And with quite a lot of research over 10 or 15 years, it was shown that these intense radio emissions from the center of galaxies are associated with supermassive black holes. So radio observations did not prove that supermassive black holes exist in galaxies, but they provided the first strong indication that some highly non-thermal phenomena and some highly compact objects or in the centers of galaxies doing energetic things. So those were two great successes of radio astronomy. Radio astronomy also was able to map out the spiral structure of the Milky Way galaxy, another thing that was done over half a century ago. Because optical light does not travel through the galaxy, it's extinguished by the dust in the plane of the galaxy. We can't see to the galactic center, for example. But radio waves travel freely and are unabsorbed. And so radio telescopes have been used to map the entire disk of the Milky Way galaxy right through the galactic center to the other side and show what its rotation is, and in a sense also help show that there was dark matter out there. So radio telescopes were also useful in the detection of dark matter. So I'm giving you an impartial list, an incomplete list rather, but there's a lot more than that. So radio astronomy is a very powerful tool of astronomy, and it's a niche, if you like. The number of radio astronomers is probably 5 or 6 times less than a number of optical astronomers, but it's provided very important insights into the high energy universe, also the cold universe, also the dense universe or compact objects. So I think that overall is a pretty strong testament to the power of that field of astronomy.
All right, it is 10:59, and so this will be our last question for today. This comes from an email. Kumar's asks, considering that telescopes are like time machines, could a telescope in the future observe the very first group of galaxies that ever formed after the Big Bang?
I think we're trying to do that right now with the James Webb Space Telescope. The James Webb was designed to measure first light, and first light is the formation of the first stars and galaxies in the universe. We know it now to have occurred probably 100 to 200 million years after the Big Bang, which is very early in the history of the universe, first 4 or 5% of the age. So I think that is on the cards. I mean, the boundary of high redshift objects and early objects in the universe is pushed further and further by James Webb every year, even though it's only been operating for a couple of years. So I think, finding these large look-back time objects is a very active field of research, and James Webb is close to cracking that problem of telling us when the first light actually was. So thanks for that question and the good variety as usual. And I'm on a trip for a couple of weeks, so I think we're probably a month before our next session, Matthew can say.
Yes, that's correct. Our next live session is 4 weeks from now in August. I don't remember the exact date, but if you are not on our courses and not receiving our emails, then join our listserv. Scroll back up to the top of the chat. There's a Google listserv link that you can join, and you'll get announcements about upcoming live sessions. Or make sure you like our video today and subscribe to our channel so that you get future announcements about upcoming live sessions. That's the best way to stay in touch with us for those upcoming Q&A sessions. So thank you all so much for joining us today. We appreciate your time, and we hope that you have a good rest of your week and weekend. Take care, everyone.